This one is 2.23. Here there is a structure shown here, and in this structure this member AB right here is rigid and this BC member is elastic in nature. We need to figure out the vertical deflection at point B because of this load 400 newtons. So let's look at the forces at this joint B. So there will be a force in this member here, there will be a force in this one. So this is FAB and this one is FBC. So from the force balance in the y direction we can write down FBC. If this angle right here is theta, FBC sine theta is equals to 400. So this gives us the value of force FBC as 400 divided by sine theta newtons. Now if you need to find out the deflection, your delta BC is going to be the force FBC times length divided by elastic modulus and A. Now this information about L over EA for member BC is given through another case when the complete load 400 Newton is applied on this BC member. So if I consider this case right here, your delta is equals to 400 Newtons times L over EA, which is same for this member, and this deformation is given to you as 23 millimeters right here. So from this we can pick up that your EA over L value for member BC is 400 divided by 23 newtons per millimeter. Now I can use that information here. So your delta BC now becomes, if I substitute 400 over sine theta for the force and L over EA coming from here, which is in the denominator, we are going to have 400 divided by 23. So this is 23 divided by sine theta in millimeters. Now this is the deformation which is going to be in member BC. Now let's try to visualize the final deformed position of this point B. This point B is associated with these two members. This one is your AB and this one is your BC right here. Now because of BC's deformation, and if you assume the deformation is happening along the length, this point will try to move somewhere here. Let's call that B1, and assuming that this C is fixed around here, to have this deformation we can be anywhere around this circle. Similarly, if AB is a rigid member, assuming that it follows that AB length, your B point could be anywhere around this circle. Now the intersection of these two circles should give us the final point, but in an approximate manner, if you assume that these deformations are less, these circles can be approximated with straight lines here and straight lines there, right? On this triangle right here, we have already calculated this value is delta BC. If this angle is theta, this angle is going to be 90 minus theta, and this right here is the vertical deformation that we need to figure out, and let's mark this as final value of B2. From this triangle you can see that your delta V is equals to delta BC divided by sine theta. So if I substitute the value of delta BC, this comes as 23 over sine square theta, and from the dimensions given, your sine theta value is square root of 4.6 square minus 3.6 square, that's the vertical height, divided by 4.6. So if I substitute all of this here, your value of delta V comes out as 59.34 millimeters.